Hello my dear students, welcome back to my channel. Hope you all are doing good. Today I am coming with one short revision of class 11th physics of chapter 10, that is mechanical properties of fluids. In this chapter I will discuss different topics like pressure due to a fluid column, then Pascal's law and its applications. This topic is very important. Then effect of gravity on fluids, pressure, viscosity, Stokes law and terminal velocity. This topic is also very important. After that, types of flow, that is streamlined and turbulent flow. Then critical velocity, Bernoulli's theorem. This topic is also very important. After that, surface tension and surface energy. Then angle of contact, excess pressure across a curved surface. This topic is also very important. And at last, bubbles and capillary rise. So I will discuss each topic one by one. Let us start first. What is this chapter name? Mechanical properties of fluids. What is this fluids? Fluids are any substance which can flow. Any substance which can flow. It has no definite shape and size. It takes the shape of the container in which it is placed. And these fluids are of two types. One is liquids, another one is gases. Liquids are those fluids which cannot be compressed. It means it has fixed volume, definite volume. It cannot be compressed. And gases are those fluids which can be compressed, right? So it has no definite volume. It means volume is not fixed, no definite volume. And you know, density is equal to mass by volume. Density is mass by volume, right? So these liquids can be compressed, cannot be compressed, sorry. So it has a definite volume, fixed volume. It means density is mass per unit volume. If volume is fixed, it means density is also fixed. So liquids are those fluids which has constant density, right? Constant density. And gases are those fluids which can be compressed. It means its volume changes. Its volume is not constant, no definite volume. And if volume is not constant, it means density is also not constant. Here density is variable, right? So in this chapter I will discuss about this liquid type of fluids, and in the next chapter we will discuss about gases. Okay, so let us start. There are two types of fluids, that is fluid statics and fluid dynamics. In fluid statics we will study about fluids at rest, and in fluid dynamics we will study about when the fluids are in motion. Okay, so let us start with that topic. So now I already discussed about fluid. What is fluid? It is a substance that can flow, and it is of two types. One is liquid and the one is gases. Liquids are those fluids which cannot be compressed, and those substances which cannot be compressed, it means volume is constant. And gases are those fluids which can be compressed. It means volume is variable, it is changing, right? So volume is constant, you know, density is mass per unit volume. If volume is constant, then density is also constant. So density is also constant in case of liquids, and density is variable in case of gases. Now there are two branches of fluids. One is hydrostatics, or this one, fluid statics, and the one is hydrodynamics or fluid dynamics. What is hydrostatics? It's a study or branch of physics in which we study about the fluid at rest. Like in this one we will study about hydrostatic pressure, Pascal's law, Archimedes principle, surface tension, etc. And hydrodynamics or fluid dynamics, dynamics means when the fluid are in motion. So study of fluids in motion comes under this hydrodynamics, and this one we will study about Bernoulli's theorem, equation of continuity, etc. Right? Now most important topic, first one is thrust in this chapter. What is thrust? When you study about the liquids or fluids, now you must know what is thrust. You know, here first I will discuss in this chapter that when the liquids are at rest, it means hydrostatics, and after that we will discuss about hydrodynamics when the fluids are in motion. So suppose there is a container in which the fluid molecules are in equilibrium, it means they are at rest, and when the fluids are at rest, due to thermal equilibrium, what happened? It exerts force on the walls of the container. They are randomly moving inside the conductor, and it exerts force on the walls of the container, and this force is always perpendicular to the surface. So this force perpendicular to the surface, it is called thrust. And it only possible when the fluid are at rest. when the fluid are in rest, what happens? It exerts force in all possible directions perpendicularly, normal to the surface. So thrust is total normal force exerted by a liquid at rest on a given surface in contact with it, right? And this, what is pressure? When fluid exerts thrust on the surface of the container, and you know thrust or force per unit area is called what? Pressure. So pressure in case of fluids is nothing but thrust or normal force exerted by a liquid at rest per unit area of a surface in contact. So pressure is thrust per unit area of normal force per unit area. Its SI unit is what? Force is in Newton, area is in meter square, so Newton per meter square, you can say Pascal, small pa. And this pressure is a scalar quantity, right? This is a scalar quantity, something written here. And what is dimensional formula? Force, you know, dimensional formula for force is what? ml t minus 2, and area is what? L square. So it becomes ml minus 1 t minus 2. ml minus 1 t minus 2 is its dimensional formula, and this pressure always acts perpendicular to the surface of contact. So these are about what is thrust and what is pressure in fluids. Thrust per unit area is called fluids. So please take a screenshot of this one. Now SI unit of pressure is Pascal, and there are some other units of pressure like atmosphere, bar and torr. In 1 atmosphere, how much Pascal? 1.103 into 10 to the power 5 Pascal. In 1 bar, 10 to the power 5 Pascal. In 1 torr, 133 Pascal. You must remember this conversion, right? After this, there are some practical applications of pressure. You know, pressure is what? Thrust per unit area, normal force per unit area. Smaller the area, greater the pressure exerted by the fluids, right now. So like first example is a sharp knife cuts better than a blunt one. A sharp knife has what? It has smaller surface area in contact, so it exerts more pressure and it cuts very easily. That's why a sharp knife cuts better than a blunt one, right? Second, pins and nails are made to have pointed tip ends. Why? So that it exerts more pressure on the walls on which it is placed. Then it is difficult for a man to walk on sand while a camel walks easily on sand. It is observed that camel's feet has a larger area so that it exerts less pressure and they can walk easily on sand. But as compared to this camel, man's feet has smaller area, so it exerts more pressure on the sand and they are not able to walk easily on the sand. So these are some practical applications of pressure. Other applications are also there. You must know, you already discussed these things in, I think, in class 9. Now after this, next one is density. What is the density? Density is mass per unit volume and it is a scalar quantity. Its SI unit is what? Kg per meter cube, and its dimension is ml minus 3. Now after this, there is an important term, that is relative density, or you can say specific gravity. What is this relative density? You know, density of water at 4 degrees Celsius is fixed, right? Because liquid is an incompressible fluid, its volume is constant, so its density is also constant at especially at 4 degrees Celsius, right? And if you want to find density of other substance, you must know about relative density. What is this relative density? Relative density is density of a substance divided by density of water at 4 degrees Celsius. It just gives idea about how much a given substance is heavier than that of the given volume of water. It just gives idea. If relative density is 4, it means density of a given substance is 4 times heavier than that of water. If relative density is 2, it means density of a substance is 2 times heavier than density of water. It just gives comparison that how much it is heavier than a given volume of water. It is a dimensionless positive scalar quantity, and density of water, you know, at 4 degrees Celsius 10 to the power 3 kg per meter cube, or in gram 1 gram per centimeter cube. When temperature increases, what happens? This density decreases. When temperature increases, molecule comes in random motion, its volume increases, then its density decreases. So there is a relation between temperature and density. So these are about this units of pressure, density and relative density. Please take a screenshot of this one. Then we will discuss next Pascal's law. Now Pascal's law. This law and its application is very important, right? This law tells how pressure can be transmitted in a liquid. It can be stated in number of ways. First one is, if we ignore gravity, pressure is same at same height. Suppose this is a U-shaped tube and in this one liquid is filled, right? So here point A and at point B, at both point pressure is same. It means at equal height pressure is same. If we ignore gravity, pressure is same at same height. This is first point. Now this second point is very important and this can be used in many applications. What is this? The change in pressure applied to an incompressible fluid. Incompressible fluid means we already discussed that it is liquid, not gas, right? So the change in pressure applied to an incompressible fluid is transmitted undiminished. Undiminished means without any loss to other parts and to the walls of the container, right? Suppose this is hydraulic lift. Hydraulic lift we discussed in detail also. Here at this point pressure is applied. This piston moves down, force is applied. Inside this one liquid is filled. So at this point pressure is, suppose some pressure P is applied, right, at this point A. Now this pressure is transmitted undiminished to other parts. It means at all parts and walls of the container. This pressure is same. Here P, here P, here P. At all points pressure is same. It is transmitted to other parts also. And here at the other end this area is large. So this pressure into large area, it exerts force F2 and it is used to carry heavy loads. We will discuss this in hydraulic lift in detail. So this second point is very important. What is this? The change in pressure applied this side to an incompressible fluid is transmitted undiminished to other parts and to other walls of the container, right? Suppose change in pressure is applied at this point, so it is transmitted equally to other parts and walls of the container. Now the third point is the pressure is transmitted equally in all directions. Suppose at this point, what is the direction of pressure? So it is equally transmitted in all directions. This is third point, and this point shows that pressure is a scalar quantity because it is equally transmitted in all directions. Actually pressure is what? Force per unit area. Here force is a vector quantity, this area is a vector quantity, but this pressure is a scalar quantity, and this point explains why it is scalar quantity, right? So these are about Pascal's law, 3 important points. You must remember all these points, and this second point is very important. This one is used in many applications. Now applications of Pascal's law. First one is hydraulic lift. What is this hydraulic lift? It is used to lift heavy object like car at a service center by applying small force. So it acts as a force multiplier. Force multiplier, right? So this hydraulic lift is based on the principle that when a small force is applied over a small cross-sectional area, then due to transmission of pressure, a large force appears at the other end where area is large, and this is used to support and lift heavy loads. What is this construction? It consists of 2 cylinders, right now, having cross-sectional area. One cylinder has cross-sectional area A1 and the other cylinder has cross-sectional area A2, right? And this cylinder is fitted with a movable piston, and inside this cylinder liquid is filled, and these 2 cylinders are connected by a horizontal pipe. Now what happens when a small force is applied at this end? F1 force is applied. So it means F1 pressure is applied over this liquid, and this pressure exerted over a liquid is given by P1 equal to F1 by A1. Now according to Pascal's law, this change in pressure applied to an incompressible liquid is transmitted undiminished to other parts and to the walls of the container. It means this pressure P1 is transmitted to other parts also. So this P1 pressure is transmitted to this other end also. Here cross-sectional area is very large, A2. So how much force it exerts over this piston? Upward force exerted on large piston is F2, and it is equal to pressure into area. Pressure is this P1. P1 into A2, and this pressure is F1 by A1 into A2. So this much force is exerted by the liquid over this piston, and this force F2 is very larger than F1. How? Here this A2 is greater than A1. It means this force 2 is greater than force 1, and this force is used to carry or support or lift heavy load which is kept over this piston second, right? Hence heavy load placed on larger piston is lifted up, and in this way this hydraulic lift works. By applying a small force, large force is created at the other end which is used to support or lift heavy loads. So this is the construction and working of this hydraulic lift. Please take a screenshot of this one. After this, we'll discuss second application, that is hydraulic brakes. Now, second application of Pascal's law is hydraulic brakes. It is also very important. What is this? It also works on principle of Pascal's law. When a pressure is applied on a fluid, it is equally uniformly transmitted in all directions, right? Now, what happens? This is construction of this hydraulic brakes. This one is master cylinder, and this is in this master cylinder liquid is filled, that is called brake oil, right? And this master cylinder is connected to this brake pedal through the piston, and this master cylinder is connected to the wheels of the vehicle. I am only drawing one vehicle. To other vehicles this is also connected. In this vehicles, what happens? This master cylinder is connected to these two pistons. There is this one is brake shoe, and this is rim of the wheel. Now what happens when this brake pedal pressed? When brake pedal this is pressed, it pushes this piston to the master cylinder, right? And a pressure is exerted on the liquid here inside the master cylinder, and this pressure is transmitted equally to all parts of this one, right now. So when brake pedal pressed, it lever pushes the piston into the master cylinder. Now the pressure is transmitted to the piston P1, P2 through this oil, right? This is oil, brake oil is what? Liquid. Through this liquid, this pressure is transmitted to P1 and P2. Now, due to this pressure on P1, P2, it moves the brake shoe. These two are connected to the brake shoe of the wheel. It pushes the brake shoe away from each other and towards the rim of the wheel, and it retards the motion of the wheel. The piston pushes the brake shoe away from each other, retards the motion of the wheel. Now, what happens? Here, this master cylinder has a small cross-sectional area. So, a small force is applied through this brake pedal, and this rim of the wheel has large cross-sectional area. So, a small force is applied through this brake pedal, and large force is created over here to stop the wheels of the vehicle, right? So that the driver safely drives the vehicle. When pedal is released, what happens? When these pedals are released, then what is spring? This is connected to these two pedal pistons are connected to these springs. It pushes the brake shoe away from the rim. When the pedal is released, it pushes this brake shoe. This spring pushes the brake shoe away from this rim of the wheel and towards each other, right? Now the piston moves towards their normal position. Due to this spring, when the spring is released, this spring pushes the brake shoe away from this rim and it comes to their normal position, and after that this piston moves towards the normal position. Oil is forced back into the master cylinder again. In this way this hydraulic brakes works. Main aim is what? Only small force is applied at this side through the brake pedal, and this master cylinder has small cross section area, but due to Pascal's law it transmitted, this fluid transmitted the pressure through in all directions through this piston also, and here this cylinder has large cross section area, so it produces large force to stop the rim of the wheel and driver can drive easily under control, right? So this is about hydraulic brakes. Please take a screenshot of this one, then we'll move to the next topic. Now next is pressure exerted by a liquid column. You know liquid exerts pressure on all sides of the container, right now. So when a liquid is filled inside this container, suppose height of the liquid is h. Due to this height h, what is the pressure exerted by this liquid? So pressure exerted by a liquid column is what? Pressure is force per unit area. Area of this container is suppose A. Now this weight of the liquid is how much? This is mg. M is the mass of the liquid, g is acceleration due to gravity. So weight of the liquid column becomes m into g. But how you find this mass of the liquid? You don't know. You know density of the liquid is constant because liquid is what? Incompressible fluid. Its volume is constant. Density is mass per unit volume. If volume is constant, density is constant, so you can easily find from this one mass. So mass becomes how much? Density into volume. You can write in place of mass volume into density into G, where this is density or rho is density of liquid. This is the force or weight of the liquid column or force exerted by the liquid column. Now this pressure, it means equation 1 becomes force per unit area. It means force is how much? AH rho G by A cancel. It becomes rho GH. So the pressure exerted by a liquid column of height h is rho GH. It depends upon the height of the liquid column. So you must remember this one. It's very, very important. This, right? Now after this one, next is variation of pressure with depth. How pressure changes with depth. Suppose if you place some object inside the liquid, now how much pressure exerted by that object due to the depth of the liquid, right now. So here suppose there is a container in which liquid is filled, and so you consider one cylindrical portion, this one of height h. This is h is the height of this cylindrical portion, right? And from the top surface, this upper point is at height x and this is h. So from the top surface total height is how much? This becomes, from the free surface, this becomes x plus h, right? Now these liquids are at rest, so liquid exerts pressure and force in all directions, but at equal height pressure is same. So net horizontal force, suppose it exerts normal force on this liquid, exert this side also, from upward also, downward also. So these horizontal force are equal in magnitude but opposite direction, and they are at equal height. So net horizontal force is 0, net pressure is also 0. Only force is along vertical direction from upward and downward. So there must be some pressure difference in the vertical direction. Force only along vertical direction. So there must be pressure difference. Now how you find this pressure difference due with this depth? Suppose this first part is at height x from the free surface. So pressure exerted by this one is at the first point is what? P1 equal to x rho g. From the free surface distance height is x, right? Now at this point pressure P2, total height is how much? From the free surface x plus h. H is the height of this container, right? So this P2 is x plus h rho g. Now this P2 is at greater height than P1, so P2 must be greater than P1 because pressure is what? Rho GH, depends upon the height of the container. Greater the height from the free surface, greater is the pressure exerted at that point. So P2 minus P1 becomes this h rho g. Here you find that when you place any object inside the liquid, pressure only depends upon the height of the container, right? It does not depends upon the height from the free surface. It only depends upon the height of the container, and here pressure difference is h rho g. If this top surface is free surface, it means this is open from the top. It means free surface means air. So if top of cylinder is air, then replace this P1 by PA, and this PA is called atmospheric pressure, pressure exerted by the atmosphere, and also replace this P2 by P. So this equation becomes P minus PA equal to h rho g, or you can write P equal to PA plus h rho g. So this P is actual pressure at height h at this point, right? So actual pressure at height h is greater than atmospheric pressure by rho gh. Total pressure at this P2 is greater than atmospheric pressure by how much? Rho GH. H is the height of the container, right? Now here three different types of pressure comes. One is atmospheric pressure, one is actual pressure or total pressure, and one is difference between these two pressure, that is gauge pressure. So I will discuss different types of pressure after this one. Please take a screenshot of this one. Hope it's clear to all of you. Pressure exerted by a liquid column, this one, and variation of pressure with depth, it only depends upon the height of the container. Whatever height is, does not depend upon the free distance from the free surface, right? And this pressure at any point is greater than atmospheric pressure by rho GH. Please take a screenshot of this one, please, fast. Now types of pressure. There are three types of pressure: atmospheric pressure, absolute pressure, and gauge pressure. What is this atmospheric pressure? Pressure exerted by the atmosphere. Suppose there is a vessel in which liquid is filled. So at the top point of this liquid, it means at the free surface, this atmosphere exerts pressure, and this pressure is called atmospheric pressure. It is represented by, written as PA, and 1 atmospheric pressure, you can say 1 atmosphere is equal to 1.013 into 10 to the power 5 Newton per meter square Pascal at sea level, and this atmospheric pressure is measured by an instrument called mercury barometer. It is filled with mercury. Next one is absolute pressure and gauge pressure. Students mainly confuse between these two types of pressure. What is absolute pressure and then gauge pressure. Okay, suppose you want to find pressure at any point inside the liquid, suppose at the bottom of this point. So at this point pressure is due to this atmospheric pressure plus, suppose this is liquid column is of height h, and you know pressure due to a liquid column is given by what? H rho g. So at this point total pressure is pressure due to atmospheric pressure plus due to this liquid column h, and this total pressure exerted at any point in a fluid is called absolute pressure. Actual pressure, atmospheric pressure plus H rho g. H is the height of the liquid column. Then what is this gauge pressure? Gauge pressure is nothing but at the free surface only pressure is due to atmosphere, but when you move down and when suppose at the bottom of the surface pressure increases as the height or depth increases, pressure increases. So how much pressure is increased? That increase in pressure or that excess pressure is called gauge pressure. The excess pressure, and that excess pressure is exerted by what? At the free surface only atmosphere exerts pressure, that is called atmospheric pressure, and when you move down due to this liquid column pressure at this point increases. So this excess pressure due to a liquid column is called gauge pressure. Excess pressure exerted by the liquid, and it is given by what? Total is this one, total pressure is this one, total pressure minus atmospheric pressure. So gauge pressure is total pressure minus atmospheric pressure. It is given by H rho g. It is just pressure difference directly proportional to H, and it is measured by an instrument called open tube manometer. It is also filled with mercury, right? So these are just small definitions, and then this next topic is hydrostatic paradox. What is this? Suppose these vessels are of different shapes, but in all these vessels liquids are filled at the same height. So at the bottom of these vessels, suppose at point A, B and C, all liquids are filled with at a height h only. So you know according to Pascal's law, liquids at equal height exerts equal pressure. So pressure at B equal to pressure at B equal to pressure at C. So the pressure exerted by liquid column depends only on this height h. P is what? H rho g, and not on the shape of the vessel or quantity of the liquid contained in this vessel. It only depends upon the height h of the liquid, and this unexpected observation is called hydrostatic paradox, right? So these are just small topic. Please take a screenshot of this one. Now next topic is buoyancy, then Archimedes principle, law of flotation. Actually this topic is deleted for this year, but still I am going to discuss because it is very important for other exams also. Let us first discuss what is this buoyancy and buoyant force. When any body is partially or fully immersed in a liquid, suppose this is a body and it is fully immersed in this liquid. Now what happens? When you placed any body in a liquid, it displaces some amount of water, amount of liquid. Suppose the level of this liquid rises by this amount and the volume of displaced this liquid is suppose V. So this displaced liquid exerts some upward force on the body, and this upward force is called buoyant force. The upward force acting on a body immersed in a fluid is called upthrust or buoyant force, and this phenomena is called buoyancy. Now depending upon this upthrust and weight of the body is always acting in downward direction, and upthrust is acting in upward direction. Now depending on this upthrust and weight of the body, a body may sink, a body may float partially or fully, right? Okay, next is Archimedes principle. What is this? Suppose this body is partially or fully immersed in this fluid, then it experiences this upward force, that is called upthrust or buoyant force. And what is the value of this upthrust? It is equal to weight of the liquid displaced. When body is placed, some amount of liquid displaced, this level of the water rises, and the volume of this displaced liquid is equal to weight of the body. Suppose density of this liquid is rho and density of this body is sigma and its volume is V. So the weight of the liquid displaced is equal to this upthrust. So you can write this one. When a body is partially or fully immersed in water, then it experiences an upthrust, and this upthrust is equal to weight of the fluid this displaced. And how you find this upthrust? It is equal to weight of the liquid displaced. Weight means m into g, and this m is mass of liquid. How you find this mass of liquid? This displaced liquid, right? So mass is what? Volume into density. Density is density of liquid. Right now volume is volume of liquid, and you can say volume of this body also, because it is equal to the weight of the liquid displaced. So this upthrust is equal to V rho g. And if sigma is density of the body, then weight of the body is equal to what? This volume of the body, sigma into g. This is weight of the body, this one is upthrust experienced by this body due to this displaced liquid, right? So this is Archimedes principle, and depending on its value, whether W is greater than U, W is less than U, depending on this one, a body may float, sink. So this is law of flotation. It states that body will float in a liquid if weight of the liquid displaced is equal to or greater than weight of the body. If weight of the body is equal to or greater than that upthrust, then what happens? Body will float. So upthrust is always acting in upward direction and weight in downward direction. If this upthrust is less than weight of the body, it means weight of the body is greater, then body will sink. If this upthrust is equal to weight of the body and fully immersed in this fluid, then the body floats. If this upthrust is greater than this weight of the body, it means body is partially immersed and body floats. So these are different conditions, and this is law of flotation. So please remember these points. These are very, very important for other examinations also, right? Please take a screenshot, then we'll discuss next topic. Now, next topic is viscosity. Up to last topic, we discussed about fluid statics, hydrostatics, when the fluid is at rest. But from here, I'm going to start fluid dynamics, hydrodynamics, when the fluid is in motion. Now, what is this viscosity? Suppose this is a fixed horizontal surface and liquid is flowing over this fixed horizontal surface. All the layers, all different layers are moving parallel to this fixed surface, and the layer which is in contact with this fixed surface has zero velocity, and when you increase upward slowly, then its velocity increases, and velocity at the uppermost layer, it means at the free surface, the liquid layer has maximum velocity. It means velocity of different layer is what? Different. All these layers are moving with different velocity. So what happens? Upper layer try to accelerate the lower layer, and this lower layer try to retard the motion of the upper layer. So this dragging force, a backward force comes into play which try to destroy the relative motion between different layers, and that property of liquid is called viscosity, right? Viscosity is a property of liquid by virtue of which it opposes the relative motion between different layers. Because different layers have different velocity, both layers try to oppose the relative motion, right? And that opposing force is called viscous force, like friction in motion. Friction, like whatever role played by friction in motion chapter, same role is played by here viscosity in this fluid motion, right? Hope it's clear to all of you. What is this viscosity? It is a property of liquid by virtue of which it opposes the relative motion between different layers, and that opposing or resistive force is called viscous force. Now next is coefficient of viscosity. What is this? You know, viscous force is a dragging force, backward force which try to resist the motion, relative motion between different layers, right? So what, on which factors that viscous force depends? Suppose this is a fixed surface, fixed horizontal surface, right? And I am considering here two different layers, this first and this second, and each layer has area, this A, and the lower layer is moving with velocity V, and when you increase, when you move towards the upper layer, its velocity increases. So its velocity increases by dv amount. So this upper layer has velocity v plus dv when you move through a distance dx, right? So that viscous force depends upon, it is directly proportional to area of cross section of contact layer. These two are contact layer. So it depends upon area of cross section. It also depends upon velocity gradient, how velocity changes with distance, dv by dx. This is velocity gradient. So this viscous force is directly proportional to area and velocity gradient. When you remove this proportionally constant, you get viscous force equal to eta A dV by dx. This eta is called coefficient of viscosity and it is given by this one. Eta equal to F by A dV by dx. What it measures? Coefficient of viscosity. It measures degree to which a fluid resists flow under an applied force. Up to how much degree fluid try to resist the motion, right? To flow under this applied force. This is coefficient of viscosity and its formula is given by eta equal to F by A dV by dx. F is viscous force, A is area of cross section of different contact layers and dV by dx is velocity gradient, right? What is the dimension? Dimension formula is given by this one, ml minus 1 t minus 2. How you find this one? Dimension formula for force is ml t minus 2. Area is L square and dV by dx. dV is what? LT minus 1 and dx is L. So this L cancel, again 1L cancel, M L minus 1 and this T minus 1. So dimensional formula for this one is ML minus 1 T minus 1. It's very important. Please remember the dimensional formula of this one. SI unit of this coefficient of viscosity Newton second per meter and it is called Pascal, right? And in CGS system it is called poise and 1 Pascal equal to 10 poise, right? This, what is direction of this viscous force? This viscous force try to resist the flow of fluid, flow of liquid. So this viscous force acts tangential to the surface and it opposes the fluid motion, right? Hope it's clear. This viscous force acts tangential to this surface and try to opposes the fluid motion, right? Now when your temperature increase, what happen? Temperature increases, then velocity of different layers also increases, and when this velocity increases, this coefficient of viscosity decreases. So how this viscosity depends on temperature? When temperature increases, viscosity decreases. This one is also very important point. So hope it's clear to all of you. Viscosity, viscous force, coefficient of viscosity. Please take a screenshot of this one. Then we will discuss next Stokes law. Stokes law. What is this? When any spherical body moves through a liquid, then what happens? It experiences some viscous force in a direction opposite to the direction of motion. Suppose this is a spherical body and it is moving through this viscous this liquid and its direction of motion is downward. Its velocity is in downward direction. So it experiences viscous force in opposite direction. It means upward direction. So this force try to retard its motion, right? And this viscous force is directly proportional to this radius of the spherical body and also velocity of this spherical body. So according to this law, the viscous force acting on a spherical body is given by Fv equal to 6 pi eta Rv, where R is radius of this sphere, V is velocity, eta is coefficient of viscosity. So you must remember this one. Now next is terminal velocity. What is this? When any spherical body moves through a viscous medium, its speed increases and it attains a maximum constant velocity. That maximum constant velocity acquired by a moving body while falling through a viscous medium is called terminal velocity. Now there are some conditions when it acquires maximum constant velocity, when net force acting on that body is 0. Suppose this is a spherical body and it is moving through this viscous liquid, right? Density of this spherical body is rho and density of this liquid is sigma. When it moves through the viscous fluid, what happens? Various force acting on this body. Weight of the body is acting in downward direction. Upthrust is acting in upward direction. Viscous force is also moving in upward direction, direction opposite to the direction of velocity, right? Now when this body acquires maximum constant velocity, it means net force acting on this body is 0. It means upward force is equal to downward force. So when this body attains terminal velocity, F net is 0, it means acceleration is 0 and it moves with constant velocity. So downward force is weight of the body, upward force is upthrust plus viscous force. Now what is the formula for weight of the body? Weight of the body is what? M into G. and this mass of the body is volume into density. Volume is 4 by 3 pi r cube. R is radius of this spherical body and density of this body is rho. So weight W equal to 4 by 3 pi r cube rho g. Upthrust, you know, upthrust is what? Upward force. This is 4 by 3 and density of liquid is sigma, so 4 by 3 pi r cube sigma g plus viscous force is given by this one, 6 pi eta rv. From here when you calculate this one, you get V equal to 2 by 9 r square rho minus sigma g by eta. This is the expression for terminal velocity, maximum constant velocity acquired by a spherical body when falling through a viscous medium. This eta is coefficient of viscosity, rho is density of body, sigma is density of liquid, r is radius of the body, spherical body, right? So this is the formula for terminal velocity, V equal to this one. Now here there are different conditions. When this first one, density of body is greater than density of liquid, it means rho is greater than sigma. In that case V is positive, and V positive means body moves in downward direction. If density of body is less than sigma, it means V becomes negative. In that case body moves upward, and when this rho equal to sigma in third case, velocity is 0 and body stops. So these are just about Stokes law and terminal velocity. Please take a screenshot of this one. After this we'll discuss next types of flow. Now types of flow. There are two types of flow. One is a streamline or laminar or steady flow, and another one is turbulent flow. What is the difference between these two types of flow? First is a streamline or laminar or steady flow. Suppose a liquid is flowing like this one. Then at a given point, each particle of the liquid follows or moves along the same path and has same velocity. Suppose at point A, every particle of this liquid passing through this point A has same velocity, suppose V1. At point B, all particles move with same velocity V2. At point C, all particles move with same velocity V3 and along the same path. Then this type of flow is called a streamline or laminar flow. The liquid flows such that each particle of liquid passing a given point moves along same path and has same velocity, right? So suppose this is all this particle has same velocity, second layer has same velocity. So this type of flow is called laminar or streamline flow. Second one is turbulent flow. Here each, suppose liquid is flowing like this one. Suppose at a particular point A, all particles of the liquid follow independent path, then do not move along the same path and also have different velocity. Then this type of flow is called turbulent flow. Here particle of liquid follow independent paths. They can move along any path and velocity of the particle is different at a given point. At the same point, all particles have different velocity. Then this type of flow is called turbulent flow, like this one. All particles have different velocity, different path. It is like zigzag. This type of flow is called turbulent. So there are two types of flow. One is a streamline, another one is turbulent. Now how you find whether a given flow is a streamline or turbulent? For that one, there is a critical velocity. Critical velocity is that velocity, it is laminar velocity of fluid below which flow is a streamline or laminar and above which flow is turbulent flow. So there is formula for this critical velocity. Suppose a liquid is passing through this tube having diameter d, its liquid density of this fluid is rho and coefficient of viscosity is eta. So then this critical velocity depends upon the diameter of the tube, viscosity and also this density of the fluid. So this critical velocity decides whether the flow is a streamline or turbulent. It is a certain limiting value below which flow is streamline and above which flow is turbulent, right? So you must remember this formula, Vc equal to K eta by rho d, where rho is viscosity, eta is viscosity, rho is density of the fluid, d is diameter of the pipe and K is a Reynolds number. This Reynolds number decides whether the flow is a streamline or turbulent. What is its value? So how you find this Reynolds number? From here K equal to rho d Vc by eta. If the value of this K is less than 2000, actually this Reynolds number is dimensionless parameter which decides nature of flow. If its value is less than 2000, then the flow is a streamline. If its value is between 2000 to 3000, then the flow is unstable. It may be streamline or turbulent flow, and if it is greater than 3000, then the flow is turbulent. This Reynolds number decides the nature of the flow, what type of nature of flow it is, right? Whether it is streamline or turbulent. So these are about types of flow, how you determine whether flow is streamline, turbulent, then critical velocity and Reynolds number. You must remember these formulas, right? Please take a screenshot of this one. So with this, I am going to end my class, because students, many topics are left, like Bernoulli's theorem, equation of continuity, surface tension, surface energy, excess pressure inside a liquid bubble, soap bubble, then capillary. All these topics are left, and if I cover all these topics in this one shot, then it becomes very lengthy and also boring. So I will try to make another part of this one shot revision of chapter 10, students. Up to then, keep revising and stay tuned with this channel. Thank you.